Homework to do all day, every day. The weekends don't really matter.
Yeah, kind of what I would say, except for, I don't know, I do like having free time with Dr.
It's like there's still just as much work.
Yeah. I'm trying to understand.
Hello. 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 Okay, let's get started. So the mic still doesn't work, so I'm gonna just keep using a higher voice volume today. So we talked about external merge sort, and to quickly recap what we said last time, we talked about this two-element sort algorithm that you can use in the first round of your external sorting algorithm, so that remember, in the base case, in path 0, what you produce is the following. You produce round size that's M over B, because you load these many pages into main memory and sort them. Okay? And how many rounds you have? Well, it's N over B over this. That's N over M rounds. Of course, you take the saving of that. So that's the base case in path 0, right? That's the base case in path 0. Effectively, what we're doing here, using two-element sort, the idea is you maintain, then each guy goes here, or then you grab the smallest, you always take the smallest value out of the H1 heap and push to the output. And for new incoming tuples, if it's smaller than the largest value in H1 heap, you push to the H2. This ensures that you always push items in order out of the H1 heap to the output. That's the basic idea of the algorithm, right? In the best case, if your input is already sorted, you can verify this. Essentially, you load the entire input once, and they go through H1 heap and being pushed to the output sequentially. And you're done sorting in linear IOs. In the worst case, what's the worst case? The worst case is the input is inversely sorted. So start with the smallest value but end with the largest value. In that case, what happens? Well, you load roughly this many pages of data into H1. The next one you try to load will always be a value that's smaller than the largest value in H1 because it's inversely sorted. So that the remaining item will always go to H2, and the max block size you can push out of H1 to the output is simply your buffer size. But that's essentially give you, in the worst case, just this. So strictly speaking, this algorithm is always going to be better than this because the run size you know is always greater or equal than minus some constant, right? Because you have to reserve some pages for the input and output buffer. If we ignore the constant, we get this condition right here. For the reason I just argued, right? It cannot be performing worse than this. So on average, of course, I didn't prove this for you. You can take this as a result. That people have shown that this algorithm, on average, give you a run size of roughly this. 2 times of your buffer size on average. Assuming, of course, we have to make some assumption here. Assumption is given a random input. Given a random input. In other words, this average is taking over the space of all possible inputs. Over all possible input, if you take the average of that, the performance of this algorithm is roughly this on average, which means the number of runs on expectation is what? Is half of this. Right? Right? Because the run size is doubled, so the number of runs must be reduced by half on average.
This might be a silly question, but could you sort of have a tournament sort and then like the inverse tournament sort at the same time that each do it, so that if it's sorted inversely, the inverse tournament sort would be the best case? Does that make sense?
What you're saying is,
so because if tournament sort is the best for when it's already sorted,
yeah,
there's probably a way to change tournament sort so that it's the best if it's inversely sorted.
well, inversely sorted, the challenge is you don't know that, right? So
Right.
you don't know that if you know for a fact ahead of time it's inversely sorted, what you should do is you load pages like this in this order, then that tournament sort still works.
Right,
So
but if you don't know, could
if
you
you don't know,
both of them at the same time and then take whichever one finishes
you mean
first?
one start from the front, one start from the end. Well, you can do that. If the output is this extreme case, yes, you end up winning, right? But if it's a random input, then you end up paying more overhead than the potential savings in my directory, right? So it's always a trade-off, right? So on average, but if you just run this algorithm blindly without knowing what input you have, on average, you can show, people prove that this gives you, on expectation, average run size of this, which means the number of runs of this. What that means is, of course, this reduces the number of passes needed to merge them, because the subsequent passes, whether you're using this or this, are identical, right? You basically merge right? Whether you're using this or this in the first round, the subsequent passes are identical. You're merging this many passes per round. Merging this many rounds per round. Okay, so that's essentially this algorithm. Now I'm gonna briefly talk about two optimizations people do for axonal sorting, right? One is called block I/O, the other called double buffer. So if you think about, let's look at block I/O first. If you think about the basic axonal merge sort algorithm we have discussed, we do one I/O per page at a time. What I mean by that is, if you look at the merging phase, forget about the first pass. First pass is okay. We're loading a block of pages into memory, sort them down to the output. We're doing block I/Os. We're not doing one I/O at a time. We're doing block I/Os. So these are sequential I/Os. But if you look at the merging phase, what do we do? Right? What exactly are we doing? We basically say, okay, we load the first page here, right? Then we merge them. You're doing one I/O per run. And these pages, remember, they're not consecutive to each other because the runs are separate from each other, right? So we load this one. With high probability, these are random I/Os you're doing. Furthermore, notice that at some point, your cursor becomes like this. At some point, right? And you need to what? You need to load the next page from the same run to that buffer page. So you will load the next page from the same run to this buffer page. And this obviously is a random I/O. So essentially, during the merging phase, you're doing random I/Os from time to time. You're not doing random I/O all the time because you have to wait for the buffer to move the cursors and merge them, right? But apart from that, you're doing random I/Os essentially. One observation is, why not we try to do sequential I/O by reading a block of pages per run every time, instead of reading one page from a run. In other words, the idea is actually very simple. So the first time, instead of loading just one page, I load, I don't know, B pages, small B pages, from the first run. These B pages obviously are random I/Os now. Oh, sorry, sequential I/Os. Follow me? Yeah? Of course, the downside of that is what? What's the downside? These B pages have to go somewhere in your memory buffer. They take space. So you no longer are merging just one page per run, you're merging B pages per run. Same for the second guy. Same for the last one. However, this can no longer be the M over B minus 1's run, obviously. How many rounds you can merge? How many rounds you can merge here? Suppose we are also doing block I/Os for the output. That's optional, right? You can still do one I/O at a time for the output, but you can choose to do B blocks of B I/Os for the output, so that you do not do random write all the time. You do sequential write of B pages at a time. Does that make sense? So if you do the calculation, what you end up with, this is for the output buffer. Is that right? Take the floor of that. That's how many rounds that you can merge. You follow me? So now the total I/O cost becomes what? Well, you still need to do the pass 0. Suppose we are using two-element sort to improve the run size and reduce the number of runs in the first pass. So we end up with half number of runs in first pass. But we need to and we merge them, and every time you can only reduce the number of runs by a factor of this much. So the base becomes this. And each run, you are still doing just a linear number IOs. So that's the new formula for this block-based approach versus the baseline approach where you do, suppose even in the baseline, I also use this optimization of two-element sort. Because a no-brainer, it always gives you better results, so why not we always use it. But then the difference is we are merging these many runs. So if you compare these two values, clearly this is always going to be larger than this, guaranteed. Because the base is a smaller number versus the log base here. However, it's a system issue, right? It's a complex system issue. You cannot simply look at two numbers and make a judgment. This one are doing a lot of sequential IOs, this one doing a lot of random IOs. So in the end of the day, who performs faster or more efficient, it's hard to tell. You really have to test your performance of your system and figure out a sweet value for B. In other words, this actually, if you think about it, this is a special case for B equal to 1. So you need to find a, so I bet the curve for most systems looks like this. So initially when you increase B, you gain some performance, right? By trading off random IO with sequential IOs. But as you keep increasing B, because you are merging less number of runs per round, you end up paying more overhead because you're doing more runs. More passes. So this is typically what we call, in computer science, when you have a curve that depends on a particular parameter value like that, and this part, the bottom part, is what we call the sweep value. Now, how do you find out your sweep value? Well, you take some trial experiment to figure out what's the sweep value for your system. Okay, so that's the first block IO thing. Next, I'm going to talk about something interesting called double buffering. Right? When I was a junior high student, right? I wrote a simple DOS program to do an animation. And one thing I noticed in my animation program is that I debug and everything runs everything runs, and I was super excited about it. But once I run it, I noticed that it has this jittering effect, meaning that the animation kind of flash. Right? It's not smooth. The reason for that, as I later found out, is that CPU is hungry for data. So your CPU is ready to process the next instruction, but your data for that instruction is not available. So CPU has to wait for the memory bus to go fetch the data, bring it to cache, so that CPU can do the computation and show the next frame of your animation. As a result of that, your animation, rather than getting a smooth experience like that, it's kind of like that. Does that make sense? So how do you solve that problem? How do you solve that problem? A fundamental technique people use is double buffering. Instead of loading one piece of data every time for CPU to process, you predict that CPU will be faster than the memory bus you can operate. So I always bring two pieces of data. The next piece of data that you expect the instruction needs, and make the data always available so that you keep CPU busy all the time. So there is a good application of this in practice, right? If you go to any of the toilet or restroom on campus, right? And how many rolls of toilet paper you see on a given day, on a given closet? 2, right? You don't see just 1. Do you follow me? Do you know why they use 2 over there? It's double buffering, right? Because you don't want to run out of paper. Does that make sense? CPU being a person in that closet, right? You don't want the CPU waiting for data at any given time. If you use just 1 roll of paper, what happens? Well, 2 things can happen. One is you run the paper in the middle of the day, which is obviously very embarrassing for the janitor, right? Second thing could happen is the janitor at night clean the toilet will say, okay, this roll is fairly low on paper, right? So what should I do? I should replace that with a full roll of paper because I don't want to run into the problem second day we run out of paper. But if you do that, you'll end up wasting a lot of toilet papers. So you always put 2 rolls of paper there. Does that make sense? So that you can afford having 1 roll completely run out of paper and second roll is still there for whatever the CPU needs. Right? Of course, this is assuming people behave normally, right? If you know that's what everyone does, we can coordinate, we can become malicious, right? In the sense that when you go to the restroom in the closet, you use the first roll. When I go, I use the second roll. We alternate. So at the end of the day, you have 2 rolls of paper. Both are low on paper. Then you're stuck, right? As a janitor, you don't know what to do, right? But typically, right? If you go to restroom, right? You notice that, I hope I typically always use the one with the smaller amount of paper on it, right? If I know what I'm doing, right? So now learning this class, I know what you should do with the toilet. So that's essentially a simple, sounds like a funny story, but that's actually a profound principle behind it, which is double buffering, right? So same thing here. Why this is related with external merge sort? If you think about it, it's actually very easy to make connection to the toilet paper example I just gave you. So going back to the case b equals 1, let's say we're not doing block IOs. So look at what the base algorithm does. You load the first page into the buffer, and you start merging them. At some point, you run out of data for that page. What do? You load the next page from the same run, but this takes time. While you're waiting for the loading of this page, can you start moving the other cursors? You cannot. Because if you do, then you can no longer guarantee this run is sorted. This merge run and output is sorted. You do have to wait for this page to be completely loaded in and reset the cursor before you can move the cursor in. That's essentially the same problem as I described earlier on that animation program I went into. Right? So what you do is you load 2 pages of data at a time from each run, so that if I run out of data in the first page, I can continue to move the cursor while the memory bus loads the next page of that run. Keep that in mind if you have taken any architecture class. In most modern computers, memory bus is not controlled by CPU. So memory bus can operate without CPU interruption, right? Meaning loading this while you moving the cursor is okay. So that you can always have that data available for you when your CPU becomes hungry, right? So that's the idea of double buffering. So you can combine these 2 ideas. Combine the block I/O with double buffering to actually the block I/O in some sense addresses this problem, right? Because you're reading a block of B pages. But the challenge, there's a subtle difference here. In the block I/O case we talked about, we load B pages at a time. So it doesn't really solve the double buffering problem because at the end of the B pages, you need to wait for the next B pages to be loaded in. So if you combine the two ideas, what happens is you load in the first phase, in the first time of a beginning of path, you load 2 B pages per run. So that when you run out of the first B pages, you can proceed without blocking your CPU to the second B pages of that run while loading the next B pages of that run into the first B pages. Does that make sense? So these two are not actually equivalent. You can actually combine the two ideas so that you get the benefit of no blocking of the CPU and sequential IOs of B pages all the time.
Are we assuming that there will be sufficient space to store all pages?
That's basically what this calculation is for, right? If you do this calculation, you make sure you have B pages per buffer, per run you try to merge, but you are only able to merge less number of runs. That's the trade-off. There's no free lunch, obviously. If you want to use 2B, obviously, suppose you only use B for the output, there's no reason for you to use 2B buffer page on the output, but you have to change this to 2B. That's the only change you need to make. When I do this, what that means is you are combining the block IO size B with the double buffering idea together. Okay. Then there's some other discussion of using B-tree for sorting, and I will skip that. You can read it yourself. Fairly straightforward stuff. Okay.
One of these days we're going to bring you lunch for free and then you can't say that anymore.
Well, it's free on me, but if you look at the whole system, if we all are part of the system, it's not free. You are paying or somebody is paying.
Okay.
If nobody is paying, something weird happening, right? So that's actually the comment you made indicates a complex of system issue. Right? System is always a trade-off between all the elements, right? If we are all selfish agent, then you cannot build a good system. Right? Selfish agent meaning each element in the system just acts on his or her own best interest, then you cannot hope for the best efficiency out of the whole system. So it's always a trade-off between this and that, depending on what's your overall objective. Okay, so now we're going to talk about query evaluation, which is going to be your lab 3, which I will release on Tuesday. Once lab 2 is due, I will release lab 3. Lab 3 is to implement different operators in a query engine, and also I won't ask you to implement the parser layer, but I will give you the parser layer. So by the end of lab 3, you will be able to type a simple SQL query and run your code and get the output. So that's essentially the objective for lab 3, which I will be releasing that on Tuesday, I believe, when you lab 2 is due. Now we're finally ready to talk about query evaluation. Right? So we talk about, let's recap what we have said. We talk about access method. We talk about storage engine. We talk about heap file, sorting file, how the pages are organized, how records are organized. We talk about indexing, hash index, B-tree index. Then we talk about XML sorting. All of these machineries are really introduced to for you to do query evaluation. So next, I will talk about query evaluation using all the machineries we have introduced so far. So a quick recap of the overall system architecture. So we have talked about these guys all the way here. Okay? So now we're going to look at these two layers. And the big picture is when you have an SQL query coming in, it goes through the parser layer. It will be passed into what we call a query plan. And then you will use the query optimizer to figure out an efficient plan, but equivalent to the input query. And then that optimized query plan will be passed to the query executor for execution. So since we like we said before, we take a bottom-up approach. So we will talk about the query evaluation first before we talk about query optimizer. In other words, we'll assume that Query Optimizer has optimized the input query and generated a query plan for you. All you need to do as query executor is take that query plan as input and execute the query according to that plan and get the results back. And then after we're done with this, we will then talk about the query optimizer, which is take the input query, then optimize it and produce a query plan for the query executor to execute. So let's recall some basic structures for single table queries. Speaking of query execution, there are a few variations we need to worry about. We have single table query from SQL. This is the structure of single table queries. Then we also have joins, right, between two tables. Then the most complex one is nested queries. Right? So we start with the basic one, single table queries. So this is just a recap of what we have. So I'm going to go through this really, really quick, because I assume that you know this SQL basics really well by now. So you can construct these different operators and put them all together to get a query like this. This is as complex as you can get for single table queries in a database system, right? As complex as you may get for single table queries, where you have aggregation, group by, having, and order by. The only thing missing here is the distinct keyword, right? You may or may not use distinct, depending on whether you want to remove duplicates from either your aggregation or your projection needs. So as I said before, this is the overall workflow for query execution in SQL. The optimizer will produce an optimized query plan, then the SQL execute that plan according to the operators involved. And I think we talked about this before in the access method part. A query plan is essentially a tree-like structure, then using the volcano model to implement each operator, right? So here is an example of it. So suppose that's my input SQL query, and I run it through my query optimizer. My query optimizer outputs this query plan to the query executor. So what it says is, okay, I'm gonna do a heap file scan first, project out only the name and GPA field of each record, rather than taking the entire content of the record, because I realized those are the only two fields needed to execute this query. Then I will do a sort by name and GPA. Then I will do distinct. Why I need to do sorting? Because if your query looks like this, then your query plan is just this. But since you have a distinct keyword, you have to do the sorting in order to remove duplicates. Like I said before, the algorithm is so that's the distributed algorithm. And we also talked about the iterator interface. This is just a recap, so I'm going to skip this. Right? The volcano model, as we discussed in the access method part. And in fact, in Lab 3, you are basically going to implement an interface similar to this for a bunch of different operators. Okay? And you implemented one already, which is the heap file scan for in Lab 1. But that's a really, really simple basic operator, right? So in Lab 3, you're going to implement some more sophisticated operators following similar interface. So here is example. I think last time I gave you example for heap file scan. Now I will give you another example for sorting. Now we understand what XML sort does. Let me show you how we can use this interface, volcano model, to implement the XML sort operator we just discussed. So we have some initialization. In the initialization phase, we generate the sorting around this, allocate this bound array and fill in with these pointers, initial number rounds, blah blah, and allocate the next RD array. So if you think about what this does, is essentially our pass through, right? So initialization is essentially is just pass through. The next, well, whenever you call next, what do you do? Well, you simply move the cursor accordingly from this next RAD array. This next RAD array, imagine these are this array size is this or this, depending on which you're using. That's the next RAD array size. And whenever you call next, I will return you the RAD, the index of of this array, pointing to a record with the smallest value that to be according to your sorting order, and then move the next RAD accordingly. And these runs hold the merged runs from each pass. And the number of runs, obviously, the number of runs is updated every pass. It's reduced by a factor of either this or this, depending on what you're using. Okay, so that's essentially how you implement this interface. Next, I'm going to give you one by one algorithms for the implementation of different operators in single table queries. Then we move on to join. So in the single table query, one basic construct is group by, right? So we have group by. So by the way, the difference of using one buffer and B buffer is this, right? This is using 1, and this is using B. Right? Essentially. Okay. So this is the block I/O.
I'm doing right now.
Still not as good as the toilet example.
So you see, in real life, people use computer science principle all the time, right? So this is a good example. Of course, what's the downside? You will think this is always good, right? The downside is much larger in size, clumsy to carry around. Well, this is easy to carry around. That's precisely what we're capturing that trade-off over there. Now, the naive approach for sort and group by is the following, right? So what you do is you do the sorting first. Of course, you sort by the group by attribute. It could be one or a list of attributes. It doesn't have to be one, right? You can group by name or group by name and ID. So you simply sort by the list of your grouping attributes. Okay. And what you do is, once you have done the sorting, so I'm talking about the implementation of this. I select some aggregate or some attribute A from the relation R, and I group by B and C. And potentially I may put that out B and C as well. So how do I implement this? The query command for this is sort, of course, by B and C. Now here is what I skip is heap from scan, and I put that out to B and C here. Of course, I need to put out A as well. In order to do the aggregation on A, then sort by B and C. Then here I do aggregate of A, and then I output I output B, C, and okay. So why this works for this query? Because once you are done with the sorting, essentially every group, all the elements for a particular group appear consecutively in this string. Right? If you view this as a string, right? Every group will appear consecutively on this screen, meaning records with the same B and C values must be consecutive from this output string to the upper operator. And then you can basically maintain a running counter for the B and C values currently you're seeing, and whenever the B and C value change, you know that's the time to start a new group. Otherwise, it must belong to the current group. Okay? So this is how you implement this using sorting. Of course, now you understand why we need to talk about external sorting, right? Because if data is big, if your size of your data is greater than this, then you have to use external sort here. You cannot use internal sorting algorithm for this part.
Is that why using a set wouldn't work? Because you could use a set to get rid of like distinct values, for example.
You're gonna use set.
I mean, that's just another example. Like, if you want to select distinct,
Oh,
so you just put all of the results in a set, and it gives you the.
Oh yeah,
the
but then the question is how do you implement this thing called set operator, right? So the way to implement that is essentially you still need to get rid of duplicate.
Right.
So what you are saying is select, not this, but select distinct of some attribute A from relation R, right? Yeah, so the way to implement this obviously is to, I think we talked about this, is to do sort.
Right. And a substitute could be set, but that, I guess that wouldn't work if you have to implement
Yeah, you have to implement
the
set.
external. Couldn't put an entire set in main memory in some cases.
Now, alternative idea to sorting for both these cases, right? This one is similar to this. Right? Instead of doing aggregation A, just put out A. Right? If that's what you're doing. Now, alternative to this is to use hashing, because sorting there is a dependency on the logarithm term, on the logarithm term. Can we do better using sorting? The alternative is to use hashing. The idea is to use this what we call the two-phase hashing algorithm. Two-phase hashing algorithm. So you can read this text, or it's easier if I may just use this graph to explain to you what this algorithm does. By the way, if you do this, I show you the difference between sequential I/O and random I/O, right? So if I have this data, sequential I/O is this, right? Random I/O is like that. Obviously, there is a difference, right? Now, two-phase hashing. So the idea is the following: you do a partition phase, then you do a rehash phase. In the partition phase, what you do is you load all the data page by page into the input buffer, and then you apply a hash function HP to hash them into n over b minus 1 output. And whenever, of course, each time you're loading just one page into the input buffer, right? So hashing this b items, because the size of the page is b, into n over b minus 1 buffers means that unless all of them go to a single output buffer, that's the extreme case. Typically, if you have a good hash function, that will not happen. These output buffers will not be filled up. But eventually, if you load page by page, you do enough hashing, one of these pages will be filled up. And what you do is you push them to the output when that happens. And then you keep doing this. Okay? At the end of the day, what do you get? At the end of the day, you get n over b minus 1 partitions in the output side of your disk. And these partitions must have variable size. They may not have the same size, depending on the distribution of your hash key values. Okay? But like I said, if you use a good hash function, like universal hash family, then highly likely you will have roughly balanced distribution to the output. Unless you have a really skewed input, meaning you have a lot of duplicates, then nothing you can do in that case. Okay? Assuming we have no duplicates, and you're using a universal hash family function, then the distribution to the output should be fairly balanced. Because the clear probability is small if you're using universal hash family.
You're not hashing the entire page, you're hashing.
You're not hashing on the entire page, you're hashing on whatever key value you choose to hash on. For example, you're doing group by, you hash based on the combination of your grouping attributes, of course. But of course, after you apply the hash, you push the entire key record to the corresponding output buffer again. But you are hashing only over attributes of interest. For attribute of interest, for sorting, that means the sorting attributes. For the grouping, that means the grouping attributes.
What happens if you have multiple keys for grouping? If you have like group by
You hash on the composite of them. For example, group by first name, last name, then your hash key is a combination of first name and last name. Obviously, okay? You always do that. Now, so that's the first phase. Now coming to the rehash phase, what we do is the following. We take all these partitions from output and now view them as your input. And what we do is we process partition by partition. So we load the first partition into your memory. And we build an in-memory hash table using another hash function called HR. So we rehash all the records from the first partition, multiple pages, of course, potentially. And we build an in-memory hash table out of them using another hash function HR. The purpose of this is to get rid of the clearance you may have from HP. Let's say HP is a universal hash family. Even if you're using a universal hashing family, it only tells you the clearance probability is small. It doesn't really get rid of clearance altogether. Suppose that clearance probability is 1%, which is not hard, right? Because the clearance probability for universal hashing is this: as long as m is greater than 100, you get clearance probability of this. Does that make sense? Now, if I use HR from another universal hashing family to build an in-memory hash table, and these two are independent from each other, right? What is the clearance probability now? Let's say the second clearance probability is also less than 1%. Then for that in-memory hash table you build, using HR for a given partition, what is the clearance probability on any one of these buckets? It must be less than this, because the two are independent, which is right? So the clearance probability is almost none. Does that make sense? Now, once you have that guarantee, you can go ahead and do a linear scan of each of these buckets to do what? To do your grouping and to do your duplicate elimination. Yeah? The trick is that one fundamental guarantee is that for any attributes with respect to your grouping list or your duplicate elimination list, they can only be in the same group if they end up in the same partition. If they are in different partitions, they cannot possibly be in the same group. Right? Because if you are from the same group, the hash key must be the same, then you must end up in the same partition. It cannot be the case that you end up in different partitions. That's why after you take one partition from the first phase into memory and build the in-memory hash table, after you have done that, you are safe to go ahead and to do your group by output. You can start outputting your values to the output without looking at, without worrying about looking at the second partition. In other words, you can do the grouping and duplicate elimination now partition by partition without worrying about combining data from different partitions. It is, however, possible that multiple groups appear in one partition because of clear. That's possible. But not the other way around. Meaning one group appear in multiple partitions. That's not possible. Okay? However, one implicit requirement for you to do this is what? Is that this partition, in the worst case, everything here is distinct. If some of them are the same, then it's a good news for you because as you are doing this hashing in an online fashion, you can start aggregating them, reduce the memory footprint needed to store your data, right? Because if you have multiple threads, if you are doing a count of the group by, then instead of maintaining 3 of the 3 values, you simply maintain a simple count, let's say for a simple count of this is the value, this is the count. So you don't need 4 space, you only need 2 space to do this. Does that make sense? You can update this count in an online fashion as well. However, in the worst case, all of these are distinct values. Then the size of your main memory hash table must be at least as big as the size of this partition. So in order to avoid doing any additional IOs, one requirement is size of one partition must less equal than the size of your buffer, which is M over B. Now, what is the size of one partition? Assuming we are using universal hashing for HP, then we can safely assume that the distribution to different partitions are balanced, unless you have a really skewed distribution, meaning a lot of duplicates. Suppose that's not the case we're dealing with. What do you do? Well, in that case, size of one partition is roughly, it's balanced, right? It's balanced. How many partitions you're producing from the first one? M over B minus 1 partitions. And for how many pages in total? Well, N over B pages in total. So that's roughly the size of one partition. So the implicit requirement for this algorithm to work is this. You get rid of the B factor, so it's N, is that right? And furthermore, we can simplify B always is the value much less than M, typically. So we can simplify this a little bit. And this implies that N must be less equal than M squared, meaning the number of items. Note that M is not the size of your buffer in pages. M is the size of your buffer in items or objects, right? The number of records you can hold in your memory must be greater than or equal to the square root for the number of items or number of records you have in your database, in your file, that you try to do group by and sorting. Or duplicate elimination also. When this condition holds, what's the cost of this algorithm? What is the cost of this algorithm? Well, you load everything once. By the end of the first phase, you push them into different partitions, but you're writing all of them once to disk. So the first phase is just this many IOs. In the second phase, what do? You load partition by partition. Doesn't matter. At the end of the day, you load each partition once. So that's another N over B. So if this condition holds, the total I/O cost for this algorithm is simply this. It's simply this. Does that make sense? Yeah. Of course, plus the output size, right? Plus T, the output size. But typically we ignore this, right? Because every algorithm has to do the output, right? So we ignore the output I/O cost. The output I/O cost is not N over B for sure, because you're producing one record per group. So it's much, much less than N over B, obviously. Does that make sense? So we typically just ignore that, because no matter what algorithm you use, everyone has to do this T I/O cost, right? T output cost. Everyone has to do it. So we just ignore that. So it's simply this. You may wonder, what if this is not the case? Typically, this is the case, right? Typically, this is the case. This square root n is a huge reduction, right? So if n equal to 10 to the power 4, square root of this is just this, 100 times reduction. Meaning, as long as your memory is bigger than 1% of your input size, you are okay. Does that make sense? Which typically will be the case. Now, what if that's not the case? For example, you are trying to use ULaptop to sort or to do group by or distinct elimination over Google data. Then it's likely this might not hold anymore. And what happens in that case? Well, in that case, some partitions might still be able to fit in your memory buffer. But the worst case, there are some partition that's really long, really big in size after the first pass. Imagine you have a somewhat skewed distribution of your input data, so that one partition has more than the other partitions. What do? Well, for all the partitions that can fit into your main memory buffer, you go ahead and proceed with the rehash phase. For those who do not fit in your buffer size, what do? Well, you apply the same two-phase hashing algorithm recursively. You simply view that partition as an input by itself and recursively run this algorithm with multiple rounds of partition and rehash. Does that make sense? You view that as an input by itself and run the same algorithm recursively on that input. How many rounds you need? Well, that really depends on the clear probability and the size of that partition. But typically, applying this one or two more rounds will get you there. Okay? So that's the idea. So I'll skip all the detailed discussions. So now we can implement this group by using this operator. When I say hash, that's essentially the two-phase hashing algorithm we talked about. You can do better. You can combine, if your goal is to do aggregation, right, or duplicate elimination, you can combine these two phases into one and introduce this algorithm called hybrid hashing. The observation is, in this two-phase approach, every partition needs to be dumped to disk and loaded back to disk in the second phase. Potentially, we don't have to do that. If inside a partition, we have many elements from the same group, and the objective is to do aggregate over them. There's no need for you to dump them to disk and load them back. Why not, in the first phase, maintain a small, meaning take this in-memory buffer and allocate a small space for it in the first phase, maintain those running aggregates for those partitions who have lot of elements from the same group. Then instead of dumping them back to disk, you can aggregate them into a single record like I showed here while you're doing the partitioning phase, so that you avoid writing this partition to disk and loading it back on to do the rehash. So that's essentially the idea. The picture is fairly simple. You combine the partition phase with the rehash phase. You allocate, and this is the trade-off you have to make. You allocate k pages, so your output buffer becomes m over b minus k, and you use those k pages to maintain a small in-memory hash table to maintain the running aggregates for those groups. Okay? So what you do is the following. You run the partition hash function. Now this partition hash function is defined as follows. I will write it out. So you define a meta hash function. And this meta hash function is, remember the partition hash function is HP and rehash function is HR. So I have two functions, HP and HR. This is for the partition. This is for the rehash. But now I define a meta hash function called HH. And this guy, take your input value x. X doesn't necessarily to be a single attribute. It could be a composite of attributes, like we discussed before. And this has the following output. It's equal to HR of x if x belongs to the in-memory size k hash table. Why? If there is already an entry of x and aggregate over some attributes, you should push this new record with value x to that and update the aggregate. It doesn't increase the space cost of your in-memory hash table. You should always push to the in-memory hash table for it. It doesn't increase the cost. There's no point of writing it back to disk and load it back on. You already have a running aggregate maintained for this value, for this group. This x actually denotes a distinct group, obviously, right? You already have an entry for this group. Don't push to disk. Update the running aggregate you have maintained so far. It doesn't increase the cost of your in-memory hash table. Or, I say this is 1, right? It also equal to HRX if 1 is false, but in-memory size k hash table still has space left. What that means is, okay, there's no entry for this group. This is a new group I have never seen before, but I still have space left for my in-memory hash table. I can create a new, then what you do, you're basically creating a new entry of x and aggregate of whatever value at HRX location in the in-memory hash table. Right? That's essentially what it is. I have space, I don't have an entry for it. It's a new group, but I have space, so I create a new entry for it, then I'm good. I call this condition number 2. What's the last case? Well, last case you have to you have to do partition, push to disk, and load that back on. If 1 and 2 are both false. Right? Now you have no choice. It's a new group, and there's no space to hold any entry for any group. So you have to partition. You have to push this entry to disk, but partition by partition and load them, and you need to do that. You need to do this phase. But the point now, even in that case, you have less number of partitions to process, because most partitions hopefully are already handled in the first phase. And the best scenario is what? This never happens. You always go with this. You may argue, okay, in order to increase the probability that this never happened, I should use a large value for k. In other words, I want to maximize the size of my in-memory buffer. What's the trade-off there? Well, there are no free lunch, right? There must be some trade-off. What's the trade-off? First of all, do you understand my question, right? Instead of use this buffer set, imagine I do a buffer set like that. What's the trade-off? The trade-off is, if you do that, you have less number of output buffers. In other words, you have less number of partitions to push record into. In other words, you increase the clearance among the partitions you produce. That increases the cost of the second rehash phase. You have way more collisions than the case when you have more partitions. Does that make sense? In the extreme case, you increase your in-memory buffer size to be almost as big as all the buffer you have, leave only one output buffer, then whatever you cannot find entry for in that in-memory buffer, they end up in one big spaghetti partition with all the collisions you can imagine. And that increases the cost of the rehash phase. Okay, that's the trade-off. Okay, so that's the hybrid hashing. Now let's talk about, we're done with single table query evaluation, because the most sophisticated one in single table query is audio by, which is done by sorting. Distinct and group by you can do using either sorting or hashing. Now we're done. We have finished this part, right? Now let's move on to more sophisticated query evaluations, like joins, right? Two table or multiple tables. Before that, I want to give you a quick preview of query optimization. You know what? I will skip this. I mean, we're going to talk about query optimization in detail anyway, so I'm going to skip this. Now, next, let's talk about still focus on query evaluation, right? Now, let's look at relational operators. These are our old friends, right? We have studied them like in greater details. And one thing, of course, that's not available in the basic form of relational algebra are these aggregation operators. But actually, we need them for supporting SQL. Now, we're going to use the same schema as we have seen from the beginning of the semester. We have the procedures and reserve. And back then, values like this bears little importance to our discussion. What's the size of each record, how many pages, and so on and so forth. It doesn't really matter back then, because the objective then is to specify what you want, but now how to do it. But now, in our context, in query optimization and query evaluation, these now become important because they impact how you're going to do it. So now we have to pay a closer attention to these values. Number of pages, number of records, so on and so forth. Let's start with simple selection queries. which is essentially of this form. I have an attribute, an operator, a logical operator, of course, greater than, equal to, and so on and so forth, which is the value over relation R. And what's the best way to execute this query? Well, the most basic form, obviously, is to do heap file scan. Right? You always do heap file scan if you have nothing else. However, now we know we also have potentially we may also have hash or tree indexing structures over your data. And if this index happens to be over the attribute you use for your selection, you might be able to utilize that somehow. Now, you may wonder why this deserves a discussion. Isn't the case that if you have an index, you always go here, you never go here? If you have an index, you always do index. That's not necessarily the case. I'll give you a simple example, okay? Imagine I'm doing the following queries. Okay, what I do is select average salary from the population, US population database table. Suppose there's a table like that, where city equal to public and age okay, like that. Now suppose I have an index. Actually, this query is fairly interesting because it's a two-dimensional query, right? It's not index, it's one-dimensional. So to simplify my discussion, let's say I focus on this one-dimensional. Suppose I have a B-tree index over age. And I also tell you it's a cluster index. The no-brainer, you should use that index to do this. Right, to answer this query. Yeah. But if I change this to this, same query, right? I just change the value of my condition. What happens if you use a B-tree? Well, it looks like this now. I mean, there's a tiny portion that's less than 1 year old. To be fair, let's reserve space for them. And there's a tiny, tiny portion of which I hope I will be there. That's above 100. So that's essentially what we do. And the portion naturally should be way smaller percentage-wise, right? If you think about it, right? It's so small that you cannot even tell there are those two portions compared to the entire US population, percentage-wise, right? So if you think about it, the cost of traversing down the tree and load, you are better off simply do what? Ignore the tree and do a heap file scan from the beginning. If you realize you're looking at all the data anyway, what's the point of going down the tree? Right? So this tells you the size of the output relative to your input size actually matter a lot in terms of optimizing your query, right? In terms of optimizing your query. So we need to know the size of the output. And formally, that's something called selectivity. We use the input size times the selectivity, often also known as reduction factor, to estimate the output size. Okay? When this value is low, for example 0.01 or 0.1, we say selectivity is high. when that value is big, like 99%, you're selecting 99% of your record, meaning the set reduction is really small, we see the selectivity is low. It's somewhat confusing. Just remember that there's an inverse correlation between the two. Selectivity is high means the output size is small. Selectivity is low means that the output size is big. Of course, this is just my convention, right? Different people use different conventions. Some other people will say when your selectivity is low, that means the output size is small. So you just need to be clear about what context, what's the convention people are using. But one major question remains is how do you estimate this? How do you estimate the reduction factor? Sometimes we can use common sense, right? If you have this, well, fine. What if I change this to Australia kangaroo? I don't know what's the age distribution for this animal look like. I honestly don't. Or I don't know. Kangaroo might not live that long. Let's say like sea turtles. I know this guy lived very long time. You know, I honestly don't know what's the select. Is it this or it's like more like that? I mean, on this side it's clear, right? It's one. But on this side, I don't know whether it's this or on this. Sometimes common sense doesn't help. Or alien stations, right? Like from Mars. How do you? I mean, I don't know. Right. So the point is, sometimes common sense doesn't work. You need to use some advanced techniques to estimate that. And later on, we will talk about this. Yeah. But for now, assuming we have some ways of doing this, and I have a segment devoted to this topic later on. Now, assuming that's the case, you know the selectivity. What do you do? Well, with no index and the file is unsorted, well, there's no choice but just do a heap file scan. Okay. With no index but sorted, you can do a binary search, as we discussed, or range search. With index and selection attribute, what should you do? Well, you have to be careful. You have to look at what kind of index you have. Is it hash index, class index, or unclassed index? So the cost really depends on the qualifying tuples and whether it's cluster or unclassed index. You actually have just done this on your homework too, like we have shown here. So you have to do a careful calculation to estimate the cost. It really depends on, again, this actually depends on the selectivity. If your selectivity is really, really high, meaning the output size is small, even if you have an unclassed index, it might still be worth using that compared to doing a linear scan. But if your selectivity is low, meaning you are outputting a lot of tuples in your range, unclassed index typically will perform worse than just simply doing a linear scan because you are doing sequential IOs versus random IOs. What about general selections? You have and or all conditions. The first thing is you convert them into what we call conjunctive normal form. Conjunctive normal form means that you have multiple terms. And they are always logically AND together. They're always logically AND together. Within each term, you have only all operators. You may have multiple alls, but you do not have AND within each term. You can prove that any logical expression can be converted into conjunctive normal form or destructive normal form. Destructive normal form is the opposite, right? All these terms are all together, and within each one you only have AND. So here we are using conjunctive normal form rather than DNF, destructive normal form. follow me? Now, I gotta simplify this discussion furthermore, meaning I'm talking about special form of conjunctive normal form, where each term has no or operators. Meaning each term is a single expression by itself, without having an or with multiple logical expressions. Okay, so that's a simplified version of conjunctive normal form. Next, I will introduce the concept of matching. Do I have to stop? Okay, I think I have to stop right here. So we'll continue from here on Thursday.